Okay, our next presentation is from Ethan Adams and Hallie Blondiau, who are students at the University of Louisiana at Lafayette.
All right, hello everybody. I'm Hallie Blondiau, and
I'm Ethan Adams. And I'm Ethan Adams.
So we come from way down south, down in Louisiana. You can see here our city is Lafayette. So around the southern region, a common plant is Tillandsia usneoides, which is also known as Spanish moss. It's kind of a hallmark of the south. I don't know if you've ever been down south or you've seen in other subtropical regions. But we want to see if there's any airborne plastic presence within these Spanish moss. So, why Tillandsia usneoides? So, these guys are really interesting. They are epiphytic, so just like your common pineapple. They live on other plants, and they are really good at trapping nutrients and other particles from the air. A lot of work is being done with them with heavy metals as well. So these guys are really cool. They have a trichome structure. So they're like organic Velcro in a sense. They're, that's what we like to call them. So they're very sticky, and they have the structure down below. This is what they look like under the microscope. You can see the trichomes and the stomata. So just like with the, oh, that's a good point right there. So yeah, you can see all these little structures here. So just like with what we've seen with groundwater, what's really, really cool about these guys is that we can use them as a way of getting a snapshot in time without the use of any pumps, specifically using it to look at airborne plastic pollutants. So we're going to kind of cut this short because we've had a lot of talks today and yesterday about where these plastics come from, but ultimately we want to look at these different fibers and beads that come off of our polyester clothing, our post and pre-production materials, and examining in the future how it affects human health. So what we started with is a preliminary study. So all to the far right there, we have a little flow chart going on of where we started. So that's our first image we ever took with our dry sample. We did notice a little bit of autofluorescing from an interesting set of pieces around our stomata, and we thought, what is this? So we went on to look into it, and we saw a couple of papers doing some artificial digestion using a wet peroxide solution. So we tried this. We did some filtration, and then we also were looking into the autofluorescence of certain plastic materials. So we did some analysis there, and we ended up with a couple of images you see at the bottom right there. So this is particularly interesting because we actually found this wasn't too effective with as small of plastics as we were looking at. And interestingly enough, the image to the bottom right, we found was free floating. So coming off of polyester, clothing, materials in the lab, things like that. But it still was interesting to us because we thought, wow, there's more in the air than we originally expected. So we have moved on to what we're going to be talking about today, getting into, okay, there's got to be something here. So with the resources that we have, we're going to be using FTIR to look at, okay, well, we found these plastics suspectedly. We're not going to do any digestion. We don't want to do any more degradation. We want to just see as good of trappers as these guys are with that Velcro-like texture that they have. What's their capability? What's the scope of their capability in trapping these plastic particles? So we created our own microplastic mixture of polyethylene and polystyrene, as well as ran a few standards under the FTIR, which we'll get into the spectra in just a few minutes. But we were able to actually infuse our own microplastics into these plants because they are so sticky, and then compare them to ones that we completely undoctored to see what the spectra would look like, just to confirm or deny if these complex molecules of plant material were any different from the known libraries that we had with the polymers.
Okay, and so in these upcoming slides, we have a few different representative images that we have taken using our FTIR microscope. And if you look here, sure, you have a lot of the other quote-unquote noise from an IR spectra, but in the fingerprint region, we can see these very distinct, at least to us and to the databases that we have, peaks. So here we have two confirmed consumer plastics, not necessarily the pure polymers, but we have these virginal microplastics that we made in the lab before running the experiment. And yes, so the fingerprint region is 1,500 to about 500, and that is what we are specifically looking at for these plastics found on the plant. So here we have some representative images of plastic on plant. One big thing that we were worried about, which we kind of saw, or which you can somewhat tell from the spectra, is the different starches and other cellular materials in the plants affecting how we can analyze these spectra. So this is two different fresh Spanish moss specimens. So in the green and the blue, we have our doctored samples, and then in the red, we have our undoctored sample. And if you look here, you can see definitely a shift, which could just be from whether or not it was a fresher sample than others, or many things like that. But in this fingerprint region, we are still seeing and cross-checking with our databases, and even subtracting out noise from extra starches. You can see the hallmarks of our plastics that we are looking at. And then this is just a composite of all of our results scaled similarly, the standards that we created, as well as the doctored and undoctored samples. So our limitations, very widespread, as I'm sure many of you in the audience know as scientists. So our preliminary results indicated that even after controlling for contamination, there is still plastic free floating in the air. And, you know, it's kind of both great and terrible, because whenever we first found plastic, after spending days refining these methods, scrubbing my arms like I was going into a surgery, wearing full cotton clothing, and just not even breathing between taking the scissors and then putting it in the paper bag, we still could not account for the sheer amount of contamination present. And then we have not used dry samples yet in our spectra, as I'm sure you could tell by the giant OH stretch here. We do still have water present in the sample, and also we are in South Louisiana, which is about 110% humidity at all times.
That's why they're there. It's why they're there.
Yes. But we also are looking into doing some more diverse samples. Currently, we have been using samples from around campus because it's easy, it's there, it's free. But we also have samples from well across the entirety of the South. I have actually recruited some of my family members into this, where we've had to take a ferry about 20 minutes out into the Gulf of Mexico before taking a 30-minute helicopter ride out to a barrier island to collect. So a lot of our samples that we have, we still need to run, but also or creating a diverse population between Louisiana and really the entire subtropical region. And then our expected future results is that our IR will remain similar and consistent with the quote-unquote standards that we have of post-consumer plastics. And then polyethylene and polystyrene will remain the most commonly found, in addition to PET, because those are one of the most abundant plastic types, as we've seen in several other presentations today. And yes, an influx of polymers may also be found based off of site, because there are some areas with higher construction, some areas with higher foot traffic as compared to others.
I also just want to add too, since being here, we've also been in talks of looking at new methods aside from FTIR that's a little bit more reliable. So we're hoping in the future to maybe refine those methods a little bit more. And we'd love to talk with any of you if you have any suggestion, any kind of feedback or comments about it, just so that way we can refine this a little more, just because this plan is so unique and such like the subtropical region. And if this is a way to, over time, get a larger snapshot without much interference, I think that would give us more resource to really expanding on airborne plastics specifically, and not just marine, as we adapted our wet peroxide oxidation solution from a marine plastic paper. These are much smaller. So yeah, I just think that's really interesting there.
But we'd just like to give out our sincerest thanks to Dr. William Schmidt and Dr. Sherry Krajewski-Self. This is all undergrad-led and funded, more or less. And the University of Louisiana Lafayette Student Government Association for paying for our conference fees, as well as our research volunteers, both past and present, and everyone here today. Without you all, none of this would be possible. With that, any questions?
I have one online. How would the preparation method affects the spectra for the mix of PS and PE? And were there any solvent used to mix these?
Yeah, so just to clarify, you mean the question is about how the wet oxidation solution could affect the IR spectra?
It's online, so you can answer as best as you can.
My understanding would be, so the solvent that we would use is, so what we've done is we've adapted it from, we would take a 30% hydrogen peroxide solution using NaCl to neutralize it, and it would have excessive heat. And I'm not exactly sure what the question really is, but if there's any clarification that you'd like to give online, that would be much appreciated.
Guys, thank you so much for the presentation. I think what's particularly interesting to me is the idea of using native biota as a mechanism for passive sampling within the environment. I think that's incredibly interesting. But you know, the data you presented is really akin to a grab sample. So I'm curious, do you think that there is some sort of way, mechanistically, that you could get a temporal resolution on the data from using this medium?
So it is very difficult to do that because what we've found, and our initial thoughts, especially when doing the artificial digestion, was that the plants were actually uptaking the plastics. So we could get a more accurate temporal scale. But what we found is, we have not found convincing evidence either from our experimentation or from some literature that has come out, which not much, about these specific bioindicators uptaking larger particles. But temporally, you can get probably about a 3-month-ish range, depending on where from the plant you grab. So they grow in one of these previous images. Let me just find it. So as you can see here, they grow on top of the tree and then just hang down. So if you take those apical, leading growth shoots and test those, you can get a more smaller time scale, but it's still very difficult based off of using it as a bioindicator temporally.
Thank you, guys. That was really interesting, and I think it's really cool research. And my question is, do you think they can act as, sinks, or they're also capturing and then releasing? And my question is because it's such an iconic moss, that if it's actually being able to take some of that and take it from the air,
Yeah.
that's a good selling point with stakeholders. And
Yeah, that's a really, I love that you brought that up, because we've had many talks about going back and forth of if we think it's maybe a bioremediator potentially. But yeah, because they're able to hold on to so much, we just recently were talking about just even the physical capabilities of that, transferring that to a technology to where maybe that could help with some remediation. The only thing is that as far as using it as a plant itself, it's only going to grow where it's very humid and hot. But yeah, transferring that technology, I think, is what's so important about this plant, especially with it being so passive. And it actually, because it's so tolerant of contaminants, it's not going to affect the health of the plant that much, makes it another really interesting point for this. So I think that is a possibility.
So I just wanted to add on kudos for the biota as a passive air sampler. It's really cool, and wanted to sort of make aware. So Minnesota has some publicly funded research by the NPCA where they are using pine needles, which drop annually as passive PFAS samplers. So they're using citizen scientists to get samples from every county. And then somebody mentioned historical data is like, we never know how we're going to use it. The Natural Resources Museum at the U has pine needle collections for each county going back decades.
Right.
They're taking select counties and they're getting a temporal look back to the when PFAS was invented to the 1950s to see a temporal, see if they can see the actual like uptake in production, actually analyzing pine needles. But I don't understand so could you explain how these things grow? You kind of like talked about the growth shoot there. So I'm trying to get my mind around that.
So these guys, they have a gametophyte and sporophyte stage. So they will essentially grow like almost starting as a little spore. They'll grow and they'll branch down. They'll extend outward and they'll just continue to grow on top of plants. They don't actually have a root system. They don't have any true leaves. They do flower at a certain point, but for the most part, they can continue to grow as much as it'll, the space will allow, but they prefer areas that are closer to water sources, which is also interesting as well with what you see with all the groundwater research that's being done. And you also see it with not high intensities of sunlight. They can't take it when it's too hot, which is also interesting considering the size in which we are seeing and what we expect to continue to see, if that answers your question.
Yeah.
Did you look at fluorescent staining?
Yes, that is one thing that we have sunk a good bit of change into.
Just tell us all about it.
Yes. So pretty much, we tried at first to do a counter stain method. So we used fluoroglucanol because our biggest issue was the plant lignin, which fluoresces very similarly. The representative image of the plastic right here is not exactly 100% accurate to what it all looks like. More often than not, it's just a lot of blue. Like in the end. But with the fluoroglucanol, the theory behind it was by doing this, we could lower the emission spectra of the plant lignin to where we can see plastic pretty much in isolation. But we've also looked into using things like Bo-Dippy, which is a lipid stain often used in neuroscience and other cellular processes, but that we suspect would have similar binding properties to these plastics. And then also Nile Red, but it's very expensive. And I will say, Bo-Dippy, which is an antibody stain, is actually cheaper than Nile Red.
We've also had extreme trouble with getting it to fix. So that's one of the things we were working on before we came here today, is trying to get the stain to fix. And we have not been able to do it successfully yet. But the hope is, if we can get it to fix, it's more convincing than just working with the autofluorescence alone. Because most of the papers that you see are going to be talking about using staining. But that's also why we kind of pivoted to FTIR, is because it was a way for us to really confirm what we were looking at without having to worry about the stain not fixing. Yeah.